several international participants also.
Bismillahirrahmanirrahim. I will formally start today's webinar. So I welcome all of our guests physically present here and present on Zoom for today's comstech webinar on implicit bias problems in high-dimensional predictive models. For today's webinar, we have Professor Dr. Syed Ijaz Ahmed with us here, physically present at comstech. He's a professor and head of the Faculty of Mathematics and Science at Brook University, Canada. And he's an internationally known scholar and established researcher. And his research interests lie in big data, predictive modeling, data science, and machine learning. To start off today's webinar, I would like to request Coordinator General of comstech, His Excellency Professor Dr. Mohammad Iqbal Chaudhry.
Auzubillahi minash shaitanir rajeem. Bismillahirrahmanirrahim. Haseeb, thank you very much. My dear brother, Professor Dr. Syed Ijaz Ahmed, a colleague of ours, distinguished participants both in person and online. Assalamu alaikum wa rahmatullahi wa barakatuh. See, we are absolutely delighted to welcome a very distinguished scholar of our own region who is serving in one of the top universities of Canada as the dean. I met Professor Ijaz some 3 years ago when I was visiting Toronto on an official trip, and I was absolutely delighted to meet Professor Ijaz. Particularly, I was very, very happy that the respect he received from his colleague in that top university and his stature as an academician, which is internationally recognized. We invited Professor Ijaz to be with us in Islamabad and then to Karachi, where he would be delivering a series of lectures to various institutions at different levels. Professor Ijaz is a very well-known academician of very high stature. He is a professor of mathematics and statistics and dean of the Faculty of Mathematics and Science at the Brock University, Canada. Before joining Brock University, he was the professor and head of mathematics at the University of Windsor and University of Regina. Prior to that, he had a faculty position at the University of Western Ontario, where he also served as a senior advisor. He's also an advisor to Sigma Analytics in Regina. He's also internationally known scholar and established researcher. His research interests concentrate on big data, predictive modeling, data science, and statistical machine learning and application in many walks of life. He connects mathematics with life, and that is the reason why his research has been widely appreciated all around the world. He has received many honors and awards from all around the world, And as we know that he is considered to be an authority in his own field and his own merit. He has been supported by a variety of grants from the Natural Science and Engineering Research Council of Canada, the Canadian Institute of Health Research, and also the Center of Excellence grant. Other sources throughout his career include NCERC grant, which was until 2017, and then renewed for another 5 years. So he has been a major recipient of very prestigious national and international grants. He has received a very prestigious international honor called Bowlang ASEAN Chair Professorship from the ASEAN countries. In University of Punjab, the largest and oldest place of higher learning in Pakistan, University of Punjab has named one of the auditoriums in recognition of his services as Dr. Ejaz Auditorium. Recently, his paper entitled Nano-Parametric Regression Estimates based on amplification technique for right sensor data received a Grand Prize Advancement Award by the International Society of Management Sciences and Engineering Science. I think the most important aspect of his research is that he covers a whole range of topics, and his core science, which is mathematics, is at work in various different kinds of development endeavors, as well as for helping the scientific research in other disciplines. His achievements are numerous, and I would not really be fair with you of spending lots of time on reading out the CV of an outstanding person. I'm sure that you would like to Google and see the achievement of Professor Ejaz. The best thing would be that I invite Professor Ejaz for his very interesting lecture on a topic. At least topic is understandable to me, and this makes lots of sense. So with this, I would like to invite Professor Dr. Syed Ejaz Ahmed for his presentation. Sir. Yeah.
Since 2012, and I have been in Canada at several places, but that's where I am for 2012. And this is the city of Niagara Falls, where I live in Niagara-on-the-Lake. So Niagara Falls is very close by to my home. It's just a few minutes drive. And so we move to the next one. So today we will be talking about the big data, which is a kind of a buzzword. Even sometimes I wonder, what does it mean and how it is defined? Next slide, please. So, okay. So there are some of the images which I took it from the Google about the big data and data science, and then the way the data is coming is not like in a data matrix, simple some numbers. It all kind of data is possible. So, and actually the big data, there is a hype cycle for emerging technologies. So big data in 2030, it was coming on the top of the hype cycle. So it's very dynamic. You can see different technologies are coming, and then you can let the students know where to go or where not to go. So in 2013, it was come to the top, and then a few years later, it started climbing down, and now it's pretty much gone there. So what does it mean? The big data is still important for us, and it is playing an important role. So this is coming from a business professor. So mostly most companies, what they do, they have data, they collect the informations, and they do some descriptive statistics. What happens? Some reports, dashboards, things like that. And then some, they go to further one more step of diagnostic. So data discovery. Why did it happen? And what we can learn from them. So for a statistician, as I'm a diehard core statistician, my field is, but I become more into data science more recently because of its application into the real life. So we do predictive modeling. So what will happen? Forecasting and simulation. So that's the most statistics department and most statisticians are very comfortable in doing predictive modeling. But prescriptive is something which we don't teach our students, especially in math and stats department or even computer science. Business schools, they do that at some business schools. Planning and optimization, what should we do next? So that's where the most important thing for any agency, either it's a government agency, public or private, prescriptive is the first thing. And then the students who knows all these four fields, they can make tons of money very easily. One of my students, she's originally from Pakistan, then Saudi Arabia, and she was a student visa. She just finished her master's. And even right after finishing her master's, she got a job in Toronto with a financial firm. And she was complaining that they didn't pay her enough, but it's almost $100,000 job. So you can make tons of money, but you need to know all these four steps. Okay, so now I will talk about my more scientific talks. And so, as I said, we heard this big data, but for a statistician, it's not high-dimensional data. The Islamabad. This is I call pre-talk, just to create the interest, generate the interest, and then I will bore you. So, all right. So implicit bias problem in high dimensional predictive models, cutting the bias. So if you remember a month ago, there was International Day of Women, and this was their theme, cutting the bias, removing the bias. So I took it from there, or I stole it from there. So about stealing, what the famous artist Picasso said, a good artist borrow the idea, a great artist steal the idea. So there are ideas are here and there. So there is nothing wrong in borrowing or stealing it. So big data. So we think if we have more information, we can do much better. Not necessarily. So I use the phrase, a word, a paradox. A paradox means two reverse conclusion may hold. You may get useful information or may not get the one. So it might be a paradox. So data needs to be extracted to make data valuable for future study or for further study. So how to extract it? So we have been doing this thing for a long time, data mining, data cleaning, even massaging the data so it can speak for whatever we want, or even integrating or torturing the data to make us whatever we want from the data, which is not something. Yeah, data torture. So you send them, you put the data in a torture cell. So basically, when you have big data, data reduction or variable selection or variable reduction is the important thing is. And we have been doing as a statistician data reduction and variable reduction for many, many decades. But what happened? Data reduction, extracting the variable informations from a big data is called the data science. That's the discipline as per my understanding in my introduction. So this is a new discipline. But basically, we have been doing data science for many years, But we are doing some part of it, computer science doing some part of it, business doing some part of it, but not together. It's called a field of data science. But to do data science, you need to know, if you want to become a good data scientist, you need to know the fundamentals or basics of math, very strong background, math, statistics, and computer science, and then the application. So nowadays, we are talking about two things: domain knowledge, subject knowledge. Before, domain knowledge may be more important, but now the subject knowledge is also very important, because you may be applying to different disciplines. You need to understand what's happening. For example, learning from networks. So you need to understand some of the things, what's happening in biological sciences and other things. So both things is important, domain knowledge and subject knowledge. So we used to have a data matrix. So N by P is some from a statistical background, they will know what I'm talking about. So you have N number of observation and P number of variables or predictors. And computer science scientists are pretty good in renaming things and giving a better name because features. So case one, sample size N is very, very large, and P number of features may not be large. So it's the volume of the data, which happens in mostly business world. Lots of data is coming, and actually data is streaming. There is no end, there is no starting point, there is no end. Data is keep coming through your cell phones. You are collecting the data, but what to do with that? Or satellite data, or even credit card data. Every second, the presence of different cash types is going on. And then the problem will be how to detect the frauds. So due to data volume, application of classical statistical methods may not be feasible. So even N is very large, P is small. The classical methods may not be stable. All the classical estimation we do may not be stable. And the case two, N may be moderate or even small with large P. So this is something new which came to us, but actually, if you recall it, we have this situation some time ago. So this is, we call in statistical terminology, we call it high dimensional data. So dimension of P is much larger, and N is very small sample. So we have few observation, and you have lots of parameters to estimate. So how to do that? So that is called high dimensional data, and which is very popular among a statistician. So all these statistical and mathematical techniques work when N is larger than P. So if you recall in our high school, when we are taking a course in linear solving the equation, and then our teacher told us, you have to have more number of equations than number of unknowns. If number of unknowns are larger than number of equations, you can't solve it. So that's the problem. And in least square, we solve the system of the problem. So that is the problem we deal with in high dimension data. So high dimension is a fancy name, but problem is, and the real example, you can think in microarray data, few people, number of genes, genomics. So there are issue with the big data. To me, main issue is the uncertainty about the data set we are using it, and the variety of data, pictures, audio, videos, text, images, how to incorporate all this information. So about the variation and about the uncertainty in data, we just, in 2019, we use a new technique, which published in Entropy in 2019. And then lots of different terminology keep coming, supervised learning, unsupervised learning. And statistics, we have been doing that through logistic regression, classification, and regression. So if you have a response variable, then it's supervised learning. If you don't have a response variable, then it's unsupervised learning. For example, ANOVA. And then lots of machine learning techniques have been introduced, which are doing for prediction modeling. Then another techniques which just people are paying more attention is called the in-sampling methods. It's coming from the Greek word a long time ago, how they formate their army. So it's divide and conquer rule. So you may have a very good data. So you take the small and then some weighted average and sample them. So we also just published one paper. And actually, this is the most recent paper with Amiri and Doxam in Tropic Journal. And sadly, I will mention Professor Doxam passed away 2 months ago. He was a very well-known professor from Berkeley and a good colleague and friend. Just giving you, as I mentioned earlier, about the example of the high dimensional data. Like you wonder how can P can be so large. So in genetic microarray studies, N is measured number of people in hundreds, and the number of features or predictors per sample exceed millions. So think about Professor Iqbal can tell me if I'm right or wrong. I got this information. The 22,500 unique proteins implies, if you get the interaction model, 253 million possible protein to protein interaction. And as they say, they have identified 42,000, a little bit more. So pretty much, you need a predictive model. So you put all this 253 million variable predictors one side and get a predictive model from other side. And then how to find which variable is more important out of 253 million. So I don't know, maybe if you heard, this is a Pakistani joke, which I talk in Europe or North America about the Indian part, that the two friends, one boy said to other, my uncle from US send us a machine, we put goat lamb one side and we get the lamb kebab from the other side. So pretty always my childhood joke, I heard it. So then the next week they again met. The other kid said, oh, my uncle from Japan said a machine, you put a lamb one side, you put a kebab one side and you get lamb from the other side. Yeah. So that's what we are doing nowadays with 253 million. Thank you. All right, so let's go a little bit more technical and talk about the model, because if you have a data, if you don't have a model, then it's a problem. Because some machine learning techniques, they do analyze the data without proper modeling. So there are some kind of friction between a statistician and computer science people on that thing, but that's okay. There has to be some rivalry. It's important to progress. It's just like a cricket team of two countries. So rivalries bring quality. All right. So we have this simple multiple regression model, the usual which we have seen for a long time. Y is the response variable, Xi is the data matrix, and beta is the parameters to be estimated. So only difference in the high dimension model, that the number of parameters, regression coefficients, are larger than aggregation. So how to deal with this problem? So sparsity. The sparsity is the name of the game. So we are not even calling the model at hand is sparse. So it means you have few predictors are important, rest of them are not important. They can be thrown out from the model. So mathematically or theoretically, we can split our regression coefficient into beta 1 and beta 2. And then we set beta 2 equal to 0, null vector. And the P1 is the number of predictors with sometimes I use one strong signals or strong influence predictors, the same thing. So now P1 is less than N. So we got some good strong signals and they are less than N, and P2 is better. So that's the trick. So it is a variable selection. So we are getting a sum model. Model with all the predictors, we are getting a sum model with only beta 1. So to me, it's a post estimation. First, we select a model, we select variables, and then we estimate the important parameters. So this is what's happening. You know, if you only look at this is the additional part. So this is the usual least square part, minimizing the square distance. And this is the called penalty function, and with different values of gamma. So this is what new techniques came, and we call it penalized regression. So for example, if gamma equal to 2, this is pretty much the ridge regression which we have been doing for decades. So but people did not realize that ridge regression can be also used for high dimensional data. But the problem is the math people will know this penalty is a square penalty. So it will calculate or estimate the number of parameters, but it will not force it towards 0. So what's the change came here? L1 now, L1 penalty. So the L1 penalty is a dimension. So it will force some coefficients towards 0. So it will produce a sparse model, a model with few predictors and a strong signal. So that's the beauty of this power. This method is called LASSO, least absolute selection and shrinkage operator. So, and then you get some models with few predictors or few features, and then they stop doing this. And they say this is it, and end of the game. But actually, it's not end of the game. You are selecting few variables from a family of huge number of variables. There might be, we may do something wrong. So that's where the bias comes into the picture. So let's dig deeper. So penalized estimation. So we, you know, this last part is called penalty part. We penalize for having more parameters. So we first model can be also called overfitted model, a model with too many parameters, and the second model can be called underfitted model, a model with few parameters. But some model estimators or underfitted are biased, because you may have forced some important one towards 0 or some non-important ones. So it's two ways. So bias is the biggest problem, I should say, in the big data. So the results we are getting with lots of bias is not good one. So we must need to control the bias. That's what I use this, the phrase cutting the bias. Either we cut the bias in our society or we cut the bias in statistical. So just look at how bias comes into the picture. So if you look at this response for expected value of y, what we're expecting, it has, we partition it x1 beta 2, x2 beta 2, and we are S1 to estimate beta 1. So that's what I put beta 1 hat, and we are taking the expected value of this. So this is equal to beta 1. If this is equal to beta 1, it's good. But you see this additional quantities, and beta 2 is there. So this is the bias. So bias will not gonna go away unless your assumption is correct that the beta 2, which you force them towards 0, they are really 0. That's where I took all this research almost 10, 12 years ago. Just that was the point. I look at it, and that point produced many PhD theses and so many small points. It's one point for research. So unless model is sparse, the bias is not going to go away. Or these quantities, they are orthogonal, but it's impossible. When you have such a big data matrix, you will have a multipolarity and collinearity. They may not. So this assumption is very unlikely and realistic. So you get some model, you will calculate its mean square error or whatever you can assess the performance. Up to certain point, this estimator will do well, and then it will go bad. So bias will increase because if some of us who know the criteria of mean square error or risk, the bias is a component. Actually, the bias is a bias square. So if it is 2, in the calculation it will become 4. So the mean square error, the risk or the prediction error will explode. So it's like you are investing your money, your pension money or whatever money your advisor tell you, you will make 5 times, but on the other hand, you can lose everything. So that's pretty risky strategy. So it's not a good trade-off between variance and bias. So I paraphrase GEP Box, who said all models are incorrect, some of them useful. So I paraphrase it. I said all some models are biased, but some of them useful. So people who don't have a basic training in statistics or some part of math, they will never understand that dropping X2 from the model, the impact will be drastic. So I can't see, you cannot see the last line. It says law of unconsciousness. You know, you become unconscious and say it will work. It's not going to work. So the law of unconsciousness will not work. So that's the message, and that's the work I started almost 12, 15 years ago. And it went very well. Now people are thinking about post-estimation, the bias problem. Even in machine learning techniques, they don't bother with the bias problem. They just get the sum model. So need to find a better trade-off between bias and variance. So need to control a bias. It's good to identify the problem at first stage. If you don't identify the problem, then how we will solve the problem? Or even if you don't accept the problem, then how we are going to solve the problem? So this is, I can make a political statement. So we have to realize what problem we have. Then we will find a solution. But if we reject the problem at first hand, we refuse to accept the problem, then we will never find a solution. So the solution is, this amount we can test it, whether statistically that there is zero null hypothesis or not zero, then we need a test statistics, all statistical work will come. And this strategy is not my strategy. It was, go back to 1944. This is called pre-test strategy. So you combine both estimators, one extreme, another extreme, combine both extreme, and the truth is always in the middle. Truth is not on one side or other side. It might be in the middle. So you combine both estimator and statistics, and this indicator function is 1 and 0. So we use the word hard thresholding. So it will either go one side or other side. So we can make a smooth function of test statistics and define a shrinkage estimator, and then the overshrinking problem can be resolved by taking a positive part of it. So it's called positive shrinkage. So basically what I did, I combined those estimators together to get a better one. So it was a Bancroft idea about pre-testing. So, and I built on it, and then Stein idea in 56 and 66 about shrinkage. So I built on this two previous idea and for high dimensional data. In fact, the Gauss was the one who offered two justification for least square. We call maximum likelihood argument and Gaussian error model, and came with the Gauss-Markov theorem. Some of us know this. Nowadays, the statistician and data science, they don't know who's Gauss-Markov and all those things. They are more into writing algorithms. So if the shrinkage estimation, it has already theoretical background for low dimension data. So I try to bring it into high dimensional data. So now my problem is how to, some model I can get it from penalized method, Lasso, Elasso, MCP, SCAD, or whatever they are available in the literature. But how to get the full model estimation? So we work with this ridge regression to get a model with more variables. So we divide into S1, S2, S3, strong, weak, and moderate. And then we use penalized method for only pick the strong signals. And then the weak signals can be included in the sparse signals or can be included with the strong signals. Theoretically, I can partition it, but when you have a data, you don't know your model will have a strong signal, weak signal, or zero signal. So there are three kinds of signals that are floating around. What is the definition of a strong? What is the definition of weak? So they're all up in the air. For example, for human heights, they talk about there are more than 20,000 genes who predicts the human height, and most of them, they are weakly contributing. So if you throw them off, you have nothing to predict. So we can get this strong signal. We can build an estimator based on the strong signal, and then you can use by least square called the restricted estimator. And then I will skip here, and we can build another one based on weighted ridge regression. So we published this paper. This is the first paper in this area, came in 2017, and then the editor decided to make a discussion paper. And the discussion paper sounds good, but it's more work. After reviewing, referring, it goes to number of people, they read it, or a very expert, and then they make a more criticism on your paper. And then we have to give a rejoinder. So we all did all this, all published. So as I said, we can get the strong signal model very simply based on like linearized method, but for including the weak signals, we go to ridge regression, weighted ridge regression, which will pick both the strong and weak signals. So there is some expression, Greek letters. So that's the weighted ridge one. And then and then more parameters come. So when you go in different direction, there are more things to be estimated. So this is the technical, this is the definition. Again, you can see some model, restricted estimator, weighted ridge, full model through a test statistics. So same formulation, what I have been doing for low dimension case. And then some more work starts. I call it, we have to calculate the risk. You can come up, suggest any estimator you like. But in the end of the day, you have to show your estimator is better than the existing one. And how we compare in terms of the risk, how much risk or mean square error involved. So we call it asymptotic distribution risk, and it's a mathematical proof. Yes, we call it mathematical proofs or creative proofs. So you can see the weighted ridge, we standardize at 1. And then the submodel, if you look at here, belongs to this delta. This delta is a sparsity parameter. Delta 0 means your model is sparse. Your assumption is correct. Then you will 1 minus something. You are doing better. But if delta is getting larger, then it's getting worse. What I would say. So theoretically, we could have also proof. And then our proposed estimator, no matter what the value of delta is, their risk will be below the 1. So that's the power and beauty of this Schwinger estimator. Regardless, your assumption is correct or not, you will still stay below or close to the line 1 of this full model estimator. If the sparsity assumption is good, then you will do much better. So that's the mathematical proof, and these are all this. So somewhere I read that the creativity is subjective. Mathematical proofs are creative, and creativity is subjective, but truth is not. So what should we do? We have been doing this thing for long. So engineering proof or artistic proof. I use the word artistic because, if you are making somebody painting, or so you as an artist, you have a control. You can make eyes bigger or cheekbones. So whatever you want to do, you can do it. So that's what called simulation. So we take the ratio of the mean square error or the risk of 2 estimator. So if this ratio is greater than that, it means we are doing better than existing methods. So now, as I said, artistic proof, I have a control to give the values of the parameters. So I pick some strong values, 1.5, 3, and 2, and then weak signals, weak values, 0.1, 0.1, and then I gave that the model is sparse. So beta 2 is 0. So let's look at the results. So you can see when P1, a strong signal is only 3. So millions of predictors, but only 3 are good one. And then the other, and the weak and 0 or 30. So you look at the values, it's 3.42. The efficiency or RMSC is much higher for the sum model. So if your model is truly sparse, you are doing well. And you will do much better than any other estimator with my suggested estimator, PSE, or the penalized method, SCART, MCP, LASSO, ALASSO. But if you see go down below, when the T is weak signal increasing, 0 signal is increasing, some models become pretty much same. But then if you go further down, the penalized methods, they are doing very bad. You can see they start doing very bad, 0.099, less than 1. So all these penalized methods, these are all penalized methods. So people are using it without thinking about the bias. So this is the problem of the bias. If the bias is taking over and the MSC is getting larger, that's why your efficiency is going down. So penalized methods are good when the model is sparse. So now let's apply on a data set. This is, since I started high dimensional, I've become more to microarray data. Lots of microarray data I have analyzed, or not, I didn't, my students did. So anyway, so in this one, there are 31,000 features and only 120 sample size. And then these people, Huang et al., they analyze this data based on LASSO and ELASSO, only penalized methods, getting some models. They picked 19 and 24 props based on LASSO and adaptive LASSO. So they are the strong signals. And the funny thing is with penalized method, you will think that 24 include all 90, may not be. And so which some models to pick based on 19 and based on 24. So that's another story. So you have to talk with the scientists. So that's what I said, domain knowledge and subject knowledge, they are both equally important nowadays. So you talk to scientists and then figure out which one to use or not. So we also, so we use the ridge regression to get a full model, and we pick one of the model with 19 and 24. So you can see 21,000 and only 19s are good. And then we calculate the prediction error. So smaller the prediction error, we are doing better. So just look at this box plot. This is the plot of the prediction error. So this is based on LASSO, penalized method based on Shedden. Look at the prediction error, how large it is. It's going from here to there, the range. And look at the prediction error range for our method, very small. So we have shown mathematically, numerically, and by data example. When you have a data, you have no luxury of partitioning it, beta 1, beta 2, beta 3. But the results will tell you that the models have lots of weak coefficients. And if you talk to scientists, they will tell that this kind of model may have lots of weak coefficients. So all three way is shown that proposed method is much superior than other one. And you can, it doesn't end. I only use the multiple regression model. You can pick any other model, generalized model, whatever model you like. So you can, the power and beauty of these techniques, it can be very easily applied to other models. All you need two estimators, full model, sum model, and then combine them together, it will work. So this is about mixed model. So mixed model, you have this another quantity, the random effect model. So X is fixed and ZI are the random one. And because in some data sets, you don't have only fixed, you may have a random effect also. So you can similarly, you can get a rigid estimator, and then you can partition, and you can get a sum model estimator. And you will get the same results, what I have shown to you. and you can build same estimator. And pretty much same way. It's the strategy is so powerful that it worked for a host of models. So once again, fMRI, brain connectivity and genetic data. So here I talk about the millions of the things. So here they are 111 sample size, over 1 million predictors, genetic data. And in this one, we did not use the penalized method. There is another way you can screen the data first, the screening methods, and select the variables. So it's a long explanation, but for a statistician, to me, is more important. I do the prediction and what my prediction is telling us. So you can see this. We use this is the important multinomial logistic regression model to do the screening. And after the screening, we got only 10 SNPs which are important. So out of millions, only 10. It's incredible. Sometimes it's a mind-boggling. When I started working in this area, I say, what's going on here? You start with million and come with tens only. But that's what it is. So then we did the same thing. We calculate the prediction error. So this is full model because I put the R because it's a regression, ridge one. This is some model prediction, and this is the relative prediction error. The smaller the error, better you are doing. And so this is pretty much one. And some model is not the less than one, so it's doing well. And because looks like it's selected some model is a good one. And then the shrinkage method, it's protective, it will protect you against bias. It's 0.93 and the positive is 0.92. And the penalized methods or regular method, lasso, a lasso, they're 0.97, 0.9. So again, our method is much better as compared to penalized methods, even for this model. So I'm just doing a book. I just came back from Turkey with working with my PhD, former PhD student. So we have, it should be coming out in a month with CRC Press. And we have many examples, many different data we have shown. So, but I will stop here. I will, and it's almost 1 hour mark. So we have generalized from low dimension to high dimension. And just there are lots of publication going on, mostly except with this child dogs, so mostly from my PhD students. And it's with working with different models, different partial linear models, generalized linear models, you name it. I mean, I don't want to do it. I don't want to publish too many papers, but once you have students, they are eager to do it. And then we have lots of conferences, special volume, books, and it's too much pressure on your time once you get something new. And so, and with different peoples, and even one we did it, matrices, statistics, and big data, it's already printed. It's old slide. So I just want to, I mentioned about there is a clash of culture between statistician and other people. So statistical science and data science, we used to pre-process sample data. We have a sample data, it was pre-processed. We used to do exact or analytical solution and goes to infinity, low dimension data analysis. We use SAS, SPSS, and R. And it's funny things that when the statistics subjects started, and we were always working with mathematician and with math and stats department, so there was always a friction between math and stats people. So a statistician will call mathematician is idealistic. And now a statistician become idealistic as compared to the data scientist. So work alone having a small team and the glory of the individuals. But things are changing because, as I said, domain knowledge, subject knowledge, you can't do alone. Big data. available from different sources. We have to frame the problem now. Before I did lots of consulting myself. Whenever I need some extra money, I will take a consulting project and I will ask the scientists, so what is your hypothesis? What is your problem? Not anymore. Business people will give you data and all they want to know how they can make more money from there. So identify the data for analysis. Is it population or sample? And so we need the new tools for new data. Python become very familiar now. And there are many, many other programs, parallel computing, but now if we have a cloud computing, but still we need to do some Hadoop, Spark, and other visualizing the complex data. I did not touch this area. That's another big area itself. And then data combining. We have been doing it for a long time. So now this new word, data fusion, record linkage. So if they link my record from code data, text data, healthcare data, and the bias problem will come if somewhere there was a mistake in algorithm and you put somebody else in your data collection. So we need high dimensional inference. We need to be pragmatic. I know agnostic is a good thing, but things time. Transdisciplinary research. It's not only just one or two areas. It's all over. And the glory of the research team. And I stop here. Thanks to all of you for attending, and thanks to Professor Iqbal Chaudhry for the invitation. And then, of course, it's without participant, it's no fun talking yourself. So, and as mentioned, my research is supported since 1998. So I'm very grateful to Canadian government for that. I stop here.
Thank you very much. That's an extremely interesting presentation. Even non-specialist like me that you thoroughly enjoyed. Sitting between two leading experts in the world, let me ask you a very naive question. See, we in analytical chemistry and also in organic chemistry, we come across lots of data sets. For instance, you mentioned about functional magnetic resonance spectroscopy. We have NMR spectroscopy. We have so much of nuclear magnetic resonance spectroscopic data. And similarly, in Genome Center, we have our colleagues working on genome data. People are working on proteomics. You mentioned about literally millions of protein-protein interactions also. Not all data is important. Not all data is equal. And not all data is reliable because they have noises, they have credibility issues. Not all protein-protein interactions are so defining. Not all genomic data physically impact the physical traits of individuals. Similarly, in data set, there are a lot of noises, in our research, we use a very, very old function called apodization factor. It is more of a Gaussian function. But the data set, which is less reliable and has more component of noise, is divided. And the data set, which is more reliable, is actually is increased in value by multiplying them by a Gaussian function. But even at the end of the day, we often feel serious problems and resolutions and others. So what are the options available? Because these are biases also.
So that is the other side of the knowledge, not from the statistician part. So that's what a statistician need to work with the scientists. And the part I didn't talk about data visualization. So that's what, when you look at those slides, you may not, there are lots of issues. So the analyze method which I was talking, you give this data to a statistician and they put the penalty parameters and all kind of things, and they get you clean models.
Okay.
So that's reliable. But the only thing which I created problem for those people by adding this weak signals thing. So they, whatever penalized method they give you, you see their prediction error are relatively small. But the problem is what you are talking is at the stage one before it's going to the statistician or data scientist is the screening one. So there are methods available, just like my student used the multinomial regression model for screening, but he should work. I mean, I guess he worked with the scientists to make sure this screening model is so they can tell with their experience whether this screening method is reliable or not. So screening is, that's what I said, the screening is, it's the first part, which when goes to statistician, they have already thought this coming from screening. So screening part, the statistician, data scientist, computer science, mathematician, all these people should work together to make sure we are not generating lots of bias. You cannot, it's just like a bias in the society. You cannot eliminate it, but you can minimize it. That's what the thing is, to minimize it.
Over to the audience, both in person, also online. And I have to leave for the airport. I would request my dear brother, Professor Dr. Tasawwur Hayat, to thank the speaker after the end of question answer. Telling you.
Yes.
6 o'clock flight, 1 hour drive.
Yeah, any questions? Is there a question? Yes, please.
To the people attending from Zoom, if you have any questions, just post them down in the chat.
Or you can
I think
also.
there were 1 or 2 people who. Yes.
What I do is normally people send in their questions later through emails.
Sure,
I
yes.
compile them and
Yeah,
I
so
forward
you
them.
provide my email address to them. Yeah, when I did the OIC one, there I get lots of emails there.
Yeah. So what I do is I'll compile them and just pass them.
Sure.
Over to you, sir. So concluding remarks.
So no one from here.
So I have a question, but it's this maybe a different question.
Sure, sure.
Actually, sir, you talk about the models and you talk about things. My question is, can you tell us the practical
If you have that, let me stand up for a second.
So this modeling part comes from the data. So whatever data you have, can come from social science, humanities, applied health sciences, or any part of the world is coming. So you look at this. So the first part of a statistician is to model building. So you can build, so any practical purpose, you can model any data. So it doesn't have to be normal. Can you? So you can say, you can model from, depends, like I give two models. One is the usual multiple regression model, when you have only fixed effect model. But the data may have also random effect. So you can model with a linear mixed model. And then there is a partially linear model. Then there is a generalized linear model. So this pretty much model in this, they will cover all kind of the data. So it's not only one data that I pick and choose and select it and fit it. So you can pretty much, if you go to the content, further, or can it's okay, we can see from there, from here. So now, so first 2 chapters are more about the introduction one, and then So chapter 3, which I talks about the chapter 2 is high dimension, then we talk about the sparse regression model. And then you go down. About 4 things I want to show you.
Yes.
So then we went into high dimension, then you see partially linear model. So you may have a data set which some components are linear, some components are non-linear. And then the down number 6, generalized linear model. When the outcome is binary, for example, logistic regression model, Poisson regression model, negative binomial. So host of models we showed in our book that we can model anything from any particular purpose. If you go further down, chapter 6, 7, and then robust regression model. So the model, maybe your data have many outliers, may not be non-normal. So still you can fit it. So it doesn't stop. So you ask a good question. So I'm selling my book here. So all I go on. And then in linear mixed model, I gave you the example further on. And you can do it for linear mixed model and then the non-linear regression model, completely non-linear. And it can go on and on. So that's enough. Thank you. So the moral of the story is that any data you have to model it properly. If it is a mixed model and you are doing with only with linear model, you will getting your model is wrong. So what do you expect? So modeling part is very important at the first stage. So make sure you are doing the correct modeling, and then the estimation, prediction, all things are in place. They are available in all literature, in books or whatever. So statistics, the famous statistician Tukey said, we are in the backyard of everybody. So there is no problem.
And modeling also depends upon the objectives associated with different assumptions and
Yeah,
conditions.
of course.
Yeah, that is always there.
Yeah.
I don't know.
So you try to
It
justify
varies person to person.
you just try to justify your assumption as much as possible. So like my whole work within 15 years was based on poking people with their assumption. You are saying the model is sparse. I say, no, model cannot be sparse all the time. Some models may be sparse. Some models may not be sparse. They may have mixed signals.
So this is research.
So maybe somebody will find some flaws in my work, and then some new research will come.
That is why we are calling it the compounding.
Yeah, exactly.
Yeah. So, any other one? So that's all. I think there is no one. So thank you very much for a very interesting lecture. If anybody has any question, then we can provide your email.
Sure.
And then one can coordinate by email. So very grateful that you spared some time.
Oh, my God.